In the figure below, line M is parallel to line N. What is the measure of angle B? Well, angle B and the 70-degree angle are supplementary, so their measures add up to 180, which means angle B would have to measure 110 degrees. What's the measure of angle J? We've already said that angle B measures 110 degrees, and angle B and angle J are alternate exterior angles that are formed by a transversal cutting across two parallel lines. That means that angles B and J have to be congruent, which would make angle J also a 110 degree angle. What's the measure of angle C? Well, angle C and the 70-degree angle are vertical angles, and since vertical angles are always congruent, the measure of angle C is 70 degrees. What's the measure of angle H? Well, angle H and the 70-degree angles are alternate interior angles that are formed by a transversal cutting across parallel lines. So those two angles would have to be congruent, making angle H a 70-degree angle. What's the measure of angle F? Angle F and the 70-degree angle are corresponding angles that are formed by a transversal cutting across two parallel lines. Corresponding angles would then be congruent, which would make angle F a 70-degree angle. Line M is parallel to line N. Find the length of segment AC. Now, since we have parallel lines in this picture, we have transversals that are creating congruent angles. So these two purple angles are congruent because they are alternate interior angles, and these two blue angles are also alternate interior angles. The two yellow angles are congruent because they're vertical angles. So what we have is two triangles that have corresponding angles that are congruent, which would make them similar triangles. And that would mean that corresponding sides would have to have lengths that are proportional. Now we'll call AC, the length of AC, x, so that we can say that the x, which is the side opposite the blue angle in the larger triangle, would have to correspond to the side that measures 5 millimeters in the small triangle. It's also opposite a blue angle. And if we look at the upper triangle, the side that measures 11 millimeters is opposite the yellow angle, as is the side that measures 8 millimeters in the smaller triangle. So that gives a proportion that we can solve, and we'll see that x measures 55/8 millimeters. Find the measures of angles A, B, and C. Well, angle C and the 130-degree angle are supplementary, so their measures add up to 180, which makes angle C a 50-degree angle. Angle B and the 60-degree angle are vertical angles, and since vertical angles are congruent, angle B has to measure 60 degrees. And we know that the sum of the angles in a triangle is 180 degrees, so to find the remaining angle, angle A, we'll subtract the measure of angle B and the measure of angle C from 180 to find that the measure of angle A is 70 degrees. Segment BC is parallel to segment DE. Find the length of segment DE. Well, since we have these two parallel segments that are being cut by two transversals, we have two similar triangles that are formed. This triangle, ABC, is similar to this triangle, ADE. So we'll be able to set up some equal ratios, some proportions that we can use to compare the lengths of the sides. For example, in this triangle, ABC, we could compare the right side to the bottom side, the 6 to the 10. And if we compare the corresponding sides in the larger triangle, the right side to the bottom side, we'll have a proportion. Now the bottom side is what we're looking for, so we'll call it X. The right side is a length of 9 meters because it's the 6 plus the 3, so we have the ratio 9 to X. If we cross multiply and solve, we'll see that X, the length of segment DE, is 15 meters. Lines L, M, and N are parallel. Find the value of X. In this case, we have two similar trapezoids that are formed. This top one and this bottom one. So the corresponding sides of those two trapezoids will be proportional to each other. So we could say that we're going to compare the right sides of the trapezoids. So we'll compare the 100 in the larger trapezoid to the 70 in the smaller. And we can compare the left sides of those two trapezoids, the 120 in the smaller to the X in the larger. If we cross multiply and solve, we'll see that X measures 84 meters. Which of these triangles are possible to draw? An acute scalene triangle can be drawn. It has three angles that measure less than 90 degrees, and all the sides are different lengths. An obtuse isosceles triangle can be drawn. It has one angle that is greater than 90 degrees and two sides which are congruent. A right scalene triangle can be drawn. It has one right angle and all three sides are different lengths. An obtuse scalene triangle can be drawn. It has one obtuse angle and the three sides are all different lengths. It's impossible to draw an obtuse right triangle. If a triangle is a right triangle, it has one right angle, and the other two angles would have to measure less than 90 degrees, since the sum of all three angles has to be 180 degrees. So we could not possibly have an obtuse angle and a right angle in the same triangle. And a right isosceles triangle is possible to draw. It's going to have a right angle and two sides that are congruent. Convert 27.86 degrees to degrees, minutes, and seconds. So we'll start by saying that 27.86 degrees is 27 degrees plus 86 hundredths of a degree. And since a degree is 60 minutes, we can say that the 86 hundredths of a degree is 86 hundredths of 60 minutes, which is 51.6 minutes. Now we'll break up the 51.6 minutes into a whole number of minutes, 51, and a fractional number of minutes, so 6/10 of a minute. And since each minute is 60 seconds, we can look at the 6/10 of a minute as being 6/10 of 60 seconds, which leads us to 27 degrees, 51 minutes, and 36 seconds. Find the perimeter and the area of the triangle. The perimeter is the distance around the triangle, which is the sum of the lengths of the three sides, which is 47 inches. The area of a triangle is 1/2 times its base times its height. The base and the height are always perpendicular to each other, so in this case the base is 19 inches and the height is 12 inches. So the area is 1/2 times 19 times 12, or 114 square inches. True or false? The sum of the angles in any triangle is 180 degrees. That is true. True or false? Triangles represented the Trinity in Christianity. That is true. True or false? A golden rectangle is a right triangle in which the ratio between the hypotenuse and the legs is the golden ratio. That is false. It would be correct to say that a golden triangle is a right triangle in which the ratio between the two legs is the golden ratio. True or false? A 3-4-5 right triangle is also called the Babylonian triangle. That is false. It would be correct to say that a 3-4-5 right triangle is called the Egyptian triangle. Find the values of x and y in the right triangle. Since this is a 30, 60, 90 right triangle, we know that there's a relationship between the shortest side and the hypotenuse. And that relationship is that if we double the length of the shortest side, we'll get the length of the hypotenuse. In other words, 2 times x would have to equal 10, which means x would have to equal 5. There's also a relationship between the length of the shortest side and the length of the other leg of the triangle, between the x and the y in this case. And that relationship is that if we take the length of the shortest side and we multiply it times the square root of 3, we get the length of the longer leg. So the x times the square root of 3 would have to equal y. And since we know that x is 5, we can conclude that y has to have a length of 5 times the square root of 3 units. Find the value of x. In a 45, 45, 90 right triangle, there's a relationship between the lengths of the legs and the hypotenuse. And that relationship is, if you multiply the length of a leg times the square root of 2, you'll get the length of the hypotenuse. Now we're trying to solve for the x in this case, and while we could divide both sides of this equation by the square root of 2 to get to our solution, we would have to do some work on the right side then to rationalize the denominator. So rather than doing that, let's try something else. Let's multiply both sides of this equation by the square root of 2. Now the reason that might help us is because the square root of 2 times the square root of 2 is equal to 2. So the left side of this equation can be rewritten as 2x. And since we're trying to solve for x, now we can just divide both sides of the equation by 2, and simplify the right side of the equation. Since 14 divided by 2 is 7, we know that x is equal to 7 times the square root of 2. True or false? If two shapes are identical except for location and orientation, then the shapes are congruent. That is true. For example, think about this triangle. If we have another triangle that is identical to it, they are congruent. And if I take the purple triangle and move it, change its location, it's still congruent to the yellow triangle. If I take the purple triangle and I change its orientation, I rotate it, it's still congruent to the yellow triangle. In fact, I could take the yellow triangle and I could reflect it across a line, and the reflection would still be congruent to the yellow triangle. Now, one thing that's going to be true if we have two triangles that are congruent is it will have pairs of sides that are congruent. So we can see in the two triangles, we have 3 pairs of congruent sides. That will give us congruent triangles. However, if we have two triangles and it's not their sides that are congruent, it's their angles that are congruent. So we have corresponding angles that are congruent in these two triangles. We do not necessarily have congruent triangles, and clearly in this case these are not congruent triangles. However, since the angles are congruent, since we have 3 pairs of angles that are congruent, we can say that we have similar triangles. That would mean that the corresponding sides are proportional. What is the order of dihedral symmetry for each figure? So what we're looking for here is the number of lines of symmetry upon which we can fold each figure and get the 2 halves of the figure to match up. The one on the left has only 1 line of symmetry, so it has first order dihedral symmetry. The figure on the right has 1, 2, 3, 4 lines of symmetry, 4 lines that we could fold this figure on, and the halves would meet up with each other, which means this figure has 4th order dihedral symmetry. Identify the properties which are associated with each shape. So, starting with opposite angles are congruent. That is a property of all 3 of these shapes. Diagonals bisect each other, also true in all 3 of these shapes. The area equals the product of the perpendicular distance between 2 opposite sides and the length of one of those sides. That is also true for all 3 shapes. That is just a fancy way of saying that the area equals the base times the height. Remember, base and height are always going to be perpendicular to each other. The diagonals are congruent. Well, that's always true in a square, not always true with a rhombus and a parallelogram. Diagonals are perpendicular. Is always true with a square or a rhombus, not necessarily true with a parallelogram. And all angles are congruent. That is always true with a square, not necessarily true with a rhombus and a parallelogram. Find the area of the parallelogram. So keep in mind that we need the base and the height, and they must be perpendicular to each other. So in this case, the base is 9 and the height is 10, and the area is base times height, 10 times 9, or 90 square centimeters. find the area of the trapezoid. Now we need to find the two parallel bases. Those would be the 6 and the 16 centimeter sides, and the height, which is perpendicular to those two sides, and that's 7 in this picture. The area of a trapezoid is 1/2 times the sum of those two bases times the height. So for this trapezoid, the area would be 77 square centimeters. Reflect the triangle across the line x equals -1. It may help if you draw the line x equals -1 in. That's a vertical line that goes through -1 on the x-axis. And reflect each of the vertices across that vertical line. So the pink triangle is the reflection across the line x equals -1. Rotate the triangle 90 degrees clockwise. Here's the rotated triangle. Now, one thing to keep in mind is that each vertex, if we're rotating 90 degrees, is going to rotate to a point that has an x and y coordinate that are switched. And then we have to consider which quadrant we're in to decide the sign of that x or y coordinate. For example, the point 13 in the original triangle is going to rotate to a point that has a value in its x-coordinate of 3 and its y-coordinate of 1. And since we're rotating 90 degrees, that would take us down to the fourth quadrant. The x-coordinates in the fourth quadrant are positive and the y-coordinates are negative. So the point 13 gets rotated to the point 3, -1. And if you rotate the other two vertices in the triangle in a similar manner, you'll end up with that pink triangle. Translate the triangle 4 units left and 3 units down. Your best bet is to take each vertex and move that vertex 4 units left and 3 units down, and then connect the 3 vertices. So the pink triangle is showing a translation 4 units left and 3 units down. The median of a triangle is a line segment which has as one endpoint a vertex of the triangle and which has as another endpoint the midpoint of the side opposite that vertex. Use a compass and straight edge to construct the median of the triangle ABC from vertex A to side BC. So the first thing we have to do in this construction is bisect line segment BC. So by putting the point of the compass on B and drawing an arc, and then the point of the compass on C and drawing an arc without changing the size of the compass, we've got two intersection points, which when we connect, we have a segment which bisects segment BC. Now that bisector intersects line segment BC at its midpoint, and if we connect up that midpoint with point A, the blue line segment is the median of the triangle. Construct the sacred cut on the square. So we're going to look at a video of how to make this construction. So I'm starting with a square already. We could have constructed this square. Instead, I'm just starting with something that is a square, although it may look a little distorted because the camera seems to be distorting this a little bit. You're just going to have to trust me that it is a square. So the first thing I want to do is find the center of this square. I want to find where the diagonals of this square would intersect. Now I could draw both diagonals in, but I'm going to, rather than cluttering up my construction so that you can see everything that's going on, I'm going to simply use my straight edge to connect this vertex and this vertex. So I am connecting 2 points, and I'll draw a line segment there. And then I'll do the same thing over here and draw a line segment there. So where those 2 line segments intersect is the center of the square, so it's where the 2 diagonals do intersect. Now the next thing I want to do is find the distance from any of these vertices to that point of intersection. Now it's going to be the same distance all the way around because these diagonals intersect at a point that is the same distance from all of the vertices. So the next thing I want to do is put the point of my compass on the vertex of the square, and I want to draw arcs that intersect the sides of the square. So there's one. Here's the second one. Oops, I think my compass slipped a little bit. There we go, that's better. Here is the third one. And notice how those are all intersecting right at this center point and the fourth one. I'm going to get the other half of it over here. Alright, so this is what's called the sacred cut. And you could draw that octagon in that you saw in the other picture if we connected up these intersections, for example this one and this one, connect those up with a line segment, do that all the way around, and you would have that octagon. Construct 2 iterations of the ad quadratum figure in the square below using a straight edge and compass. When completed, you will have a total of 3 squares, including the original. So let's take a look at how to construct the first square, and then we'll think about what you would have to do to construct the second square inside of that one. Now, just like with the last construction, we could have constructed a square, and I guess a purist would want us to do that construction, but we're going to start with a square. So if this doesn't look exactly square, once again it's because the camera is distorting things a little bit. But we have a square, 4 congruent sides, 4 right angles. So we want to nest another square inside of that, and what's important is that the vertices of the inside square have to touch the midpoints of the sides of this larger square. So I need to find the midpoint of one side at least. So what I'm going to do is just look at this line segment right here and try to find the midpoint of that line segment. So basically I'm going to think about bisecting that line segment. Now I could take that line segment, copy it off to the side, and do the construction off to the side. In this case I'm just going to do it right on this picture. So I'm going to make the compass a little more than half the distance, and I'll make an arc on either side of this line segment, and then without changing the compass I'll go down to this other endpoint and make arcs that intersect those. So now I could connect those up with a line segment, and that line segment would be perpendicular to this side of the square. But what I'm really interested in is this midpoint. So instead of, once again, cluttering up the whole picture so that you can't really see what's going on, I'm just going to do this. I'm still connecting up these 2 intersections, but this point right here is the midpoint of this line segment. So I've got a distance I can use. I can say that this distance from here to here is half the distance, half the length of this line segment. So I can copy that distance to all the other line segments by going from the vertices, which remember are points, and making arcs on these sides. And so now what I've got is 3 more intersections, which are defining 3 more points. And the 4 points that I've drawn are the midpoints of the sides of the large square. So if I connect those up, I will have an inner square that has vertices that are at the midpoints of the outer square, which will make this an ad quadratum figure. Now I could continue this if I wanted to. I could find the midpoints of the smaller square and use those as vertices for an inside square, but I'm just going to do the one square. So the video showed how to construct one square inside of the original one. But in order to complete this problem, you would have to go that one step further and construct another square inside of the first one that you constructed. And that inner square has to have vertices that are at the midpoints of the inner square. So you'd simply repeat the process using the lengths of the sides of the inner square as the sides that you need to bisect in order to get the vertices for the inside square.